Green hydrogen could help clean up industries like steel, cement, and shipping, but so far it's been too expensive to compete with fossil fuels. Electrogenos says it's cracked that problem by redesigning how hydrogen is made, using abundant materials instead of costly precious metals. Alfredo, everyone in this field says green hydrogen is too costly. How have you actually managed to make it cheaper than fossil fuels?
We had actually to break the trade-off between cost and efficiency. So what we see today on current systems is that you're trying to optimize for one of the two. Either you try to make the systems very, very efficient to utilize better the electrons, which are very expensive today, and therefore you use platinum, iridium, or very expensive membranes. But of course, that has a cost element to it. So at the end, the cost of hydrogen remains more or less the same. So you need to break that. We do that by getting systems that are 5 times cheaper to manufacture and 98% efficient. By doing both at the same time, we're able to break this cost parity with fossil fuels.
Your catalysts perform twice as well as platinum, but cost far less. What's the actual breakthrough here? Is it new materials or a smarter way of using the existing ones?
It is the latter. We actually found that mixing different materials, trying to promote the best attributes that they have, or working together, they're going to make a better profile than platinum. So if we go into the details, platinum is very good at evolving hydrogen, but it's not so good at getting the water dissociated. So we made a dual system where we tackle both at the same time. So we're doing both the water dissociation and the hydrogen evolution happen simultaneously instead of sequentially. And therefore we have like approximately double or almost 3 times more activity than platinum.
Okay, give us a picture we can visualize. What happens on your electrode that doesn't happen on a normal one?
We talk on different things, but maybe the most visual way of seeing it is most catalyst, or one of the most common problems of some electrode, is that when you evolve this hydrogen, you're converting the water or you're splitting the water into the gas. So these bubbles get stuck into the surface of the electrode, creating basically a curtain. So it blocks the active site where the reaction happen. We're able to minimize the bubble and increase the detachment. So by getting almost like this bubble self-removed instantly, we're making that the sites are constantly available, increasing the rate of reaction.
You say you can manufacture below $85 per kilowatt. That's even cheaper than China. How did you bring that cost down so sharply?
Of course, we had to make a game change. So Chinese are amazing at getting very cheap resources, both labor and cost of materials, and they're amazing at economies of scale and manufacturing. So it was clear to us that if we were going to compete on the same playing field, we were not going to succeed. So we had to change it to a technological play. So going back to the activity of our catalyst, because it's twice the activity of platinum, it means on the same space, on the same electrode, we produce double the amount of hydrogen. This means to produce the same size electrodes, the same systems, we need half the amount of electrodes. But the fun part is Chinese electrolyzers don't use platinum as some European, but they use nickel. We are 6 times more active than nickel. So actually our systems have 1/6 of the plate. So this is like the corner store of how we compete against them. We use less pieces, but also the pieces that are inside are cheaper and faster to manufacture.
You're running a 5 kilowatt system now. What's the next milestone? And when do we see this at megawatt or industrial scale?
Well, we are still a couple of years away, but at least the roadmap is clear. We have at this point stabilized the electrochemistry and architecture. So it's more of an engineering challenge where you need to scale in terms of volume and in terms of number of plates. So now we are having a more like defined roadmap where we need to slowly increase this both diameter and number of plates, but it's more of an engineering challenge than a science one, right? So we're close.
A lot of clean tech depends on subsidies. Can your hydrogen scale up on its own, or do you still need government help?
It absolutely can. We're already cheaper than gray hydrogen in many use cases. Subsidies are a force multiplier, not a requirement. By using subsidies, you can expand the number of sites where hydrogen is profitable, but that doesn't mean that today in many parts of the world and many use cases, it already is without subsidies using our technology.
Heavy industries like steel and cement run on thin margins. When does green hydrogen become the smart business choice, not just the green one?
You need to understand that in every industry, there are different segments and verticals. So of course, if you're trying to develop construction sites, new housing on developed countries or impoverished regions, it might make no sense to put this burden on them. But we're building here like massive skyscrapers and like very high-end buildings that the customers not only like demand, but require that they are green and they are sustainable.
Hydrogen has a credibility problem. We've heard this time it's different. Why should we believe it now?
We actually have demonstrated physically and practically, not only in a theoretical concept. I believe that people got super excited and they were announcing goals and targets rather than actual verifiable KPIs. we've demonstrated 98% efficiency at 3,000 amps. And we've done that in real systems tested in the fields of our partners, but also academic institutions like the National Physical Laboratory of the UK or Oxford University, where efficiencies and our costs have been validated.